So we'll get our first taste now of the geometry of linear transformations, and maybe more interestingly, what elementary row operations can kind of tell us about that geometry. So just before we took our break today, we got an introduction to what a determinant is supposed to represent. So if I have a linear transformation represented by a standard matrix, here it's 1, 1, 2, minus 2, I look at what that linear transformation does to the volume, or since this is a 2 by 2 transformation, the area of regions in the domain. And by definition, the determinant of a matrix is the factor by which the volume of something in the domain is changed when it lands in the image, or in the codomain, if you like. So here, when I apply the linear transformation to my cat face, I get a bigger cat face. In particular, I get a 4 times bigger cat face in the codomain as I had in my original domain. So my determinant should be a number whose magnitude is equal to 4. But in addition to the magnitude, the determinant also has a direction. It's a vectorial quantity, if you like. And its direction is going to be either positive or negative, depending on whether my transformation preserves or reverses orientation. And for my cat picture, I notice that since this little brown spot is on the right side of the original cat's chin, but is on the left side of the image cat's chin, that means that we are in fact reversing orientation. And so the signed area of this, of the factor by which area changes here is not just 4, it's negative 4. And so negative 4 is the determinant of this matrix. And so the question in front of us for the rest of our time together today is, first of all, how do we compute the determinant of a matrix? The 2 by 2 case is pretty quick. There's going to be a nice little formula that we can get for the 2 by 2 case. But of course, we're interested not just in the 2 by 2, but in the general situation. How can we use what we already know about linear algebra to help us compute what would be not just areas, but volumes of parallelepipeds determined by the columns of A? That's kind of what the definition of a determinant is. It's the volume of the parallelepiped that's determined by the columns of A inside of the image, inside of the codomain of our linear transformation. So how could we hope to compute such a thing? Different linear algebra textbooks have different approaches to doing this. We are going to stay away from the definition that's called cofactor expansion. So if you see that definition somewhere else, if you watch a YouTube video, if you do something, do your research, or if you've had linear algebra before and you like cofactor expansion, I'm going to encourage you to leave that aside for the rest of the semester. I noticed that when I taught this course last year, a number of people tried to use cofactor expansion instead of the method that we're going to learn, and I think that it short circuits understanding in a lot of ways. So please do try to avoid using cofactors if you're familiar with that. If you have no idea what I'm talking about, then don't worry about it, because we're going to learn a method that avoids having to use that specialized technique and actually sheds a little bit more light on what a determinant is and what it ought to mean at the end of the day. So to get us started, what I want to do is well, let's start here. One of the second most important thing about determinants, arguably it might even be the first most important thing about determinants, is how the determinant behaves with respect to the composition of linear transformations, one with another. And so here is a really important fact about determinants. Important fact. For 2 linear transformations of the same dimension, T and S, both going from, let's say, n-dimensional space to n-dimensional space. So I have 2 square matrices, basically, with standard matrices A and B. The following thing is true, and this is probably, again, arguably one of the most important facts about the determinant, and it is that if I multiply 2 matrices together, in other words, if I take the composition of my 2 linear transformations and then I measure the determinant of that, what I'm asking is, by what factor is the volume of a unit cube going to change if I first apply the B transformation to it and then I apply the A transformation to it? By what factor are we totally going to change by? So for example, if B is a transformation that doubles volume and A is a transformation that triples volume, if I compose those two things together, the volume is first going to get doubled and then tripled, and so the net effect is it's going to get 2 times 3. It's going to get 6 times, if you like. And so the statement of this fact is that the determinant of the product of two matrices A and B is the same as the product of the determinants of those two matrices, determinant of A times determinant of B. This is probably, again, the most important fact that we could possibly hope to know about determinants and how they work. And why this is useful, how we're going to make use out of this, is we're going to use this fact to come up with a way to determine the determinant of an arbitrary square matrix. And the way that we do it is we're going to go all the way back to M2. And M2 is a section where we think of row operations as matrix multiplication. So what we're going to do is develop a little dictionary for the various elementary row operations. Remember, there's 3 different types. There's a row swap, so trade places with 2 rows of a matrix. There is multiply a row by a constant, and there is add a multiple of one row into another row. Those are the 3 different flavors of elementary row operations. It turns out that we can represent each one of those row operations as multiplication by a matrix. And in doing excuse me, in doing so, what we're going to be able to do is show that every matrix is equal to some product of elementary matrices multiplied by its reduced row echelon form. Or conversely, its reduced row echelon form is equal to the original matrix multiplied by a bunch of other matrices that represent those elementary row operations. Then, if we can figure out the determinant associated with each one of those elementary row operations, and we can find the determinant of the reduced row echelon form itself, then we just have to multiply all those determinants together to get the determinant of the matrix that we're interested in. So that's the roadmap. We're going to look at how each elementary row operation can be represented by matrix multiplication, and therefore what impact do each of the elementary row operations have on the determinant of a matrix as we work it from its original form into its reduced row echelon form. It would just be the number itself. So the determinant of a 1-by-1 matrix would be just equal to the number itself.
Okay.
One of the ways to think about that is that represents a linear transformation of the real number line, which is just equal to multiplication by that number. Right? And so
Gotcha.
it's looking at how the length would be changing. If I multiply the whole real number line by 7, well, that's going to multiply all of our lengths by 7, and so the determinant should be 7. If I multiply everything by -6, then it's not only stretching lengths by a factor of 6, but it's also flipping them over the origin. And so I should get a determinant equal to -6. So that's kind of the base case, if you like, for determinants, is a 1-by-1 matrix has a determinant that's just equal to the entry of that matrix. And so even going from 1-by-1 up to 2-by-2 is already a non-trivial sort of change from a geometric perspective. And then 2-by-2 to 3-by-3 is likewise a little bit more fraught. And then every time we go up a dimension, we have to compute a higher dimensional analog of volume as we go along the way. But fortunately for us, this row operation viewpoint is going to totally streamline that process, because it's going to show us a way to sort of keep score of how the determinant of my original matrix changed as I brought it from its original form into its reduced row echelon form. So let's take a peek at what we'll be doing here in this example. So first, can I find, and we'll just do this piece by ourselves, if I were to look for a 3-by-3 matrix such that when I multiply that matrix on the left by this matrix A, that what I get on the right-hand side is the same as the matrix A that we originally started with. So let's just talk this one out really quickly. What matrix could I put here that's going to make it so that multiplication by this matrix doesn't change that matrix at all? So what we end up finding here might be called a left identity element in the algebra of matrices, right? It acts just like the number 1 would act. If I multiply 1 by any real number, it doesn't change that real number. So I'm looking for the matrix multiplication analog of the number 1. When I multiply matrices, the product that I get is going to be, the first column of the product is going to be my matrix multiplied by the first column of the second matrix. So the first column here, 201, has to be equal to my unknown matrix multiplied by 201. So a matrix full of all zeros with the exception, that on the diagonal we have 1s. Like this.
Yes.
Yeah, I would agree with this, right? Because what we're going to get is when I multiply this out, I'm going to get 2 times the first column plus 1 times the third column. That's exactly going to be 201. That's going to give me the first column of my product. My second column product is 7 times the first column plus 3 times the second column plus 1 times the third column. Well, that's exactly 7, 3, 1 because my columns are the standard basis vectors, right? So this matrix here, 1, 0, 0, 0, 1, 0, 0, 0, 1, that matrix is called the 3 by 3 identity matrix for this reason, right? That it acts just like the number 1 does. The 3 by 3 identity matrix. And often we'll denote that by I. Sometimes I sub 3 if the context is clear. Okay, so that's a matrix which if I multiply a matrix on the left by it, nothing happens. Nothing at all happens, right? We leave everything exactly the same. So that's what we're going to mean by an identity matrix. It works not just on the left side of a matrix, but also on the right side of a matrix. So here comes the fun part. This is the big activity for this section. And that is, if I make some slight tweaks to the identity matrix, I can come up with new matrices that achieve elementary row operations. For example, we can create a matrix that doubles the third row. We can create a matrix that swaps the second and third row. We can create a matrix that adds 5 times the third row into the first row. This is activity 4.2.2, and this is what I'd like for your groups to work on next. So if we want to double the third row by left multiplication via a matrix, we can do that by left multiplying by this matrix, 1, 0, 0, 0, 1, 0, 0, 0, 2. So you take an identity matrix, but you replace whatever relevant entry that you want corresponding to the row that you're trying to multiply. Replace that 1 with whatever factor you're trying to multiply that row by. And that will have the effect that we would like it to have. So let's call this the row multiplication matrix. And so I have a question. What do we expect the determinant of this matrix, 1, 0, 0, 0, 1, 0, 0, 0, 2, what do we think the determinant of that matrix is going to be? Any ideas? Like, well, how would that matrix change volume? Maybe another way to ask that is, how would the matrix 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 2, how would it change length, width, and height?
Would the height get 2 times taller?
Mm-hmm. The height would get 2 times taller. What would happen to the lengths and the widths?
They'd be the same?
Lengths and widths would remain the same. And so what would the volume totally change by?
2 times?
2 times. Right. If I double the height but the length and the width stay the same, then the volume is going to be doubled in total. So the determinant of this matrix would be 2. What happens if I put just a generic constant here, 1, 0, 0, 0, 1, 0, 0, 0, k?
K times bigger?
K times bigger. And if k happened to be negative, it would still be negative, would still be appropriate because we would be reflecting and not just stretching that length or width or height or whichever one we put it there, right? So there's what happens if I want to multiply a row by a constant. I can use a matrix that looks just like the identity, but it replaces the 1 on the diagonal with the factor that I'm trying to multiply that row by, and at the cost of the determinant being multiplied by that factor of k. So let me highlight that because that's going to be important for us moving forward. All right, so that's what happens with row multiplication. The next step is going to be to think about, what about swapping rows? Row swap matrix. So let's think about that one next. All right, so I agree with that too. If I want to swap the second and third rows of my matrix, then I can do that by multiplying by an identity matrix which has had its second and third rows interchanged. Right? That's what we have here, with a 1 in the third column, second row, and a 1 in the second row, third column, second column, third row. So let's think for a moment about what would happen to the determinant. So if I were to just take the width and the height, or like the y and the z, or whatever in this case, and I just flip-flop them, what's going to happen to the volume, and what's going to happen to the orientation of anything that I multiply that by? So the determinant of this transformation, because it preserves the volume but it reverses orientation, the determinant of that is going to be -1. So another way to think about what that's telling us is that every time we swap rows, in the process of discovering the reduced row echelon form, the determinant of our matrix along the way switches sign. It gets multiplied by -1 as we go along. So far we have the two different flavors of elementary row operations. Row multiplication, if I multiply a row in place, then the determinant gets multiplied by that number. If I swap two rows, then the determinant is going to reverse sign. It's going to go from positive to negative or negative to positive. And so the third kind of row operation that we would be interested in is adding a multiple of one row to another. This is probably the trickiest one to figure out, so play around a little bit with that. How can I achieve adding 5 times the third row to the first row via a process of matrix multiplication on the left? So I want to add 5 times the third row into the first row. 2 plus 5 times 1, 7 plus 5 times 1, -1 plus 5 times 1. So what do you think? So if our first instinct is that we want to put a 5 in that upper right-hand entry to try and accomplish what we're trying to do, right, is row 1 plus 5 row 3 gets stored into row 1, right? If I put the 5 up there, what's going to happen is that I'm going to end up going across the row down the column, right? And so my first entry up here is going to be 1 plus 5 times 1. I'm sorry, 1 times 2 plus 5 times 1. And then, let's see. So we're supposed to do the whole first row up here, right? And so the second entry is going to be 1 times 7 plus 5 times 1. And then my third entry on that first row is going to be 1 times -1 plus 5 times -1. 1 times -1 plus 5 times -1. And then all the rest of the matrix is going to remain the same. 0, 3, 2, 1, 1, -1. It's kind of hard to read. But did that do what we were expecting it to do? Actually, it kind of looks like it did, didn't it? I just had a small typo here. Okay. And what was I doing? Oh, right, because I'm adding 3 times the, right, I'm adding 5 times the third row into the first row. And so, yeah, so this matrix actually does do exactly what we hoped that it would do. So all we had to do was take our identity matrix and just change one of the zeros in it into something non-zero. So what do we think is going to happen if we take the determinant of this matrix? This is one I'll probably want to give away. Because what we're doing in this case is we're taking y and z and they're remaining the same, and x is changing to x plus 5z. So the kind of transformation that we're getting is the kind of transformation we saw a few minutes ago with 1101. We're getting a shear transformation like this one, where the area actually remains the same. We're just pushing over the square into a parallelogram, so it's sort of leaning over like a stack of papers, if you like, if you shove a stack of papers off to the side. So the determinant of this matrix is 1. And so whenever we add a multiple of one row to another row, the determinant remains the same. It gets multiplied by 1, right? Nothing changes. So this is kind of our dictionary for each of our 3 elementary row operations and what it does to the determinant of a matrix. So every time I multiply a row in place by k, the determinant of the matrix gets multiplied by k. If I swap rows at any point, then I multiply the determinant by -1. And if I add multiples of one row to another row, the determinant remains the same. So what we want to do with our last half an hour together today is to use this property, use these 3 properties as a way of computing the determinant of a matrix.